Hello, everybody. Mr. Hennon here for a little Institute notes. These are actually kind of a review of some of the things from Chapter 20 on electric circuits. So we're going to talk about some of the basics of electric circuits in here. So to start off with, an electric circuit basically just needs an energy source and then an energy consuming device, and you have wires connected through there so those electric charges can move. So now we're getting into electrodynamics. We're getting the movement of charges. In a battery, we often talk about the transfer of electrons from one terminal to the other, which we're going to get to a little bit later, and the potential difference. So in other words, the voltage difference across those terminals is sometimes referred to as electromotive force, or EMF. I'm not a big fan of the term EMF, but I wanted to bring it up because it is a term maybe you might hear sometime if you go into more electrostatics or actually electricity. So moving right along, the next idea is electric current. So electric current is the amount of charge that's going to flow through something. So we've got these little charges here, and they're flowing through some surface. So they're moving through here, whatever that charge is. And if you actually find the ratio of the amount of charge going through a particular surface divided by the time it takes, this is what we call current. And we use I to represent current because it's the intensity of the current. So it's the intensity of the flow. And 1 coulomb per second is equivalent to an amp or an ampere. So that's one of the first terms that we get when we talked about electricity and electric circuits. There is such a thing as direct current versus alternating current. It depends on whether these charges only flow in one direction or whether they go back and forth. And so that you have motion alternating. We're just going to deal with DC, so we're just going to be dealing with direct current. We won't have to worry about both of those parts. So just try a simple little idea. Let's say you have a current or you have a 9-volt battery in your pocket calculator and it draws 0.17 milliamps of current, and you want to know in 1 hour how much charge is going to flow through that circuit. So you would solve this for Q. Now I tend to get rid of the deltas on here. I tend to just write this as Q equals I multiplied by time, but the book likes to use the deltas in there. It doesn't really matter. So we converted our current into amps, so milli means 10 to the minus 3, and we multiplied by the time, but make sure we're in seconds, and you get 0.61 coulombs. The other idea that we'll get at is the idea of energy, and the way this is kind of written is funny, but if you think about it, remember potential, or the potential difference, was the electrostatic potential energy divided by charge, or a little test charge. So that's why you could actually write this as Q equals IT with a little one, because it's kind of your test charge. It's the thing moving. So if I use that, that's what they're using right here, you can find the energy of something by just taking your charge and multiplying by the voltage, or actually the potential difference. So you often talk about energy differences and potential differences, and that's what they did for the second part once we found that charge. Couple little things that pop up. This one I just left on here just as a reminder that we talk about current. Going back to Ben Franklin, unfortunately, he thought that it was moving positive fluid. So we talk about what we call conventional current, which is going to flow from a positive towards the negative. So conventional current in this system would flow in this particular direction because it starts at the positive and ends on the negative. We now know it's actually the flow of electrons. Electrons go in the opposite direction, so they're going from negative to positive. For me, I don't think it matters which way you pick as long as you are consistent with it, and I think you'll be fine. Next up is resistance. So let's say that you have some kind of light bulb and you're going to have a certain amount of resistance to the flow of charge in there, and you can find this resistance by actually taking the ratio of two quantities. With Ohm's law here, you can take the ratio of the voltage across divided by the current flowing through, and you get resistance. Often we refer to this as V equals IR. So Georg Ohm did a relationship between these two and came up with what we call resistance, which is why we name it after him. This should actually be a capital O because it's Ohm after someone, just like this should be a capital V and a capital A. I don't know why the book doesn't like to write that because we're talking about people. So a volt per amp is the same thing as an ohm. It's just a way of measuring how much it resists the flow of charge. And a resistor, which we commonly draw like this is a squiggle line, just like we draw this as a battery, is the resistance to the flow of charge and its device in there. A light bulb would be an example of a resistor. So if you knew that you had two 1.5 volt batteries, which are typical AA's or AAA's or C's or D's, and you provide the current of 0.4 amps in this filament, we could find the resistance. We would just say, okay, we've got two of them connected. That's a total of 3 volts across this resistor with zero point 0.4 amps going through it. So the light bulb must be a 7.5 ohm resistor. So just an example of Ohm's law. So we've got the definition of current and we've got the definition of Ohm's law, which relates some 3 different quantities. The other one, this one we're going to take a look at with an activity hopefully later, is how the pieces that actually affect the resistance of something. So there's 3 things that affect it. One is a thing called the resistivity. It's really what the material is made out of. Let's get my pen back. So the resistivity is what it's made out of. So if you have a conductor, it's going to have a really low resistivity. If you have an insulator, it has a really high resistivity. The other things is if you have current flowing through something, the longer the material, the longer it has to flow, and you should see a direct relationship. So the longer this is, the more resistance you're actually going to get. However, since you're talking about the flow of charge through something, another way of thinking of it is the width of it, so how big it is. So if I think of like water flowing through a pipe, the wider the pipe, the easier it is for the water to flow. The same is true of electricity. The wider the wire, the easier it is to flow. So actually here, if you increase the area, the cross-sectional area of it, you actually get a decrease in your resistance. So a couple of little things that I think are neat, and I'm hoping to get a chance to try this out. You can look up resistivities for a variety of different materials. Here we've got a whole bunch of conductors. Notice they are fairly low numbers here. We've got semiconductors, they get a little bit higher. And then you've got insulators, which are even much higher. So as you kind of vary between your different materials, it has a funny unit. It's an ohm times a meter because it's canceling out the extra unit to give you ohms. Next up, if we wanted to find the amount of power being used by something, which is the rate at which energy is being used, we are basically going to take our energy up here and divide by time to figure out power. But energy can be found by taking the charge multiplied by the voltage. I'm not really sure why they talk about delta Q. I would actually think of it as a delta V, but Q times that V. Then they're trying to point out that you've got Q over time. Q over time is the same thing as current. So we end up with a nice little relationship here that the power being used in a circuit is the current times the voltage. So it's make sure you understand the difference between these. These equations look very similar. The resistance of a material is the ratio of the voltage to the current, the voltage across and the current through, but power is the product, and it's measured in watts, which a watt is going to be equivalent to an amp times a volt. Using these 2 equations combined together, you can come up with other equations as well for finding power. I think if you just have these 2, you're good. We don't need to necessarily have all the others. They have another example here. Let's say we have the flashlight. We know how much current. We know the voltage. Can I figure out how much power is delivered? Could I figure out how much energy it uses? And we definitely could, because we could just multiply those 2 to figure out it's a 1.5 watt light bulb. This is where that wattage for light bulbs kind of comes from. The amount of current times the voltage that is across it. And then going back, that energy is power multiplied by time. They just multiply those together to figure out how much total energy it's using. That kind of runs down everything from chapter 20 that you would have had in physics 1, just kind of a quick little setup, and we'll be moving into circuits and using them with capacitors as well. So we're doing kind of a combination next week. See you then.